Hello everyone. Welcome to this lecture series on structural mechanics. In this lecture series on structural mechanics, we will study how forces are transmitted through structural systems and their effects. We begin with the trusses, which are widely used in bridges, roofs, towers, and industrial structures. Understanding truss analysis will help us determine whether individual members are in tension or compression, which is essential for safe and economical design. Today's lecture is lecture number 1 and the topic is analysis of trusses using method of joints. This lecture forms the foundation for truss analysis, and once this concept is clear, you'll be able to analyze more complex truss systems with confidence. Let us first understand what a truss is. A truss is a structural framework made up of straight, slender members which are connected at their ends by means of pins or hinge joints and are arranged in the form of triangular units. So this triangular arrangement makes a structure geometrically stable as well as efficient in transferring the loads. In an ideal truss, the loads and reactions only acts at the joints. The members carry axial forces alone, either it may be in tension or compression. Before analyzing a truss, we make certain idealizing assumptions to simplify the analysis. They are: members are connected by frictionless pin joints, loads and reactions act only at the joints, the members are straight and prismatic, self-height of the member is negligible or in no case it will be considered, each member carries only axial force, and the deformations are small so that the geometry does not change. So these assumptions will allow us to apply the simple equilibrium equations to determine the internal forces. Now before analysis, we must check whether a truss is statically determinate or not. So for a plane truss, the condition is m plus r is equal to 2j, where m is the members numbers, r is the number of reaction components, and j is the number of joints. If you are having the condition m plus r is equal to 2j, it is called, the trusses or the frame is called a perfect frame. Perfect frame or perfect truss in case of trusses. If you are having m plus r is greater than 2j, it will be called redundant truss. It will be called as a redundant truss. On the other hand, if m plus r is less than 2j, means it is called a deficient truss. So now mostly we will be going on with the perfect truss mechanism. Now in analysis of these trusses, we have two different methodologies are available. One is the method of joints and the other one is the method of sections, in addition to the graphical method. So this principle is very simple. Each joint of a truss is in equilibrium. At every joint, external loads, support reactions, as well as the axial forces in the connected members must satisfy the equilibrium condition. And for a plane truss joint, we will be satisfying this condition, sigma fx equal to 0 and sigma fy equal to 0. So this one method of joints is best suited for finding the forces in all members and becomes tedious for large trusses. Now we shall move on with a numerical problem. So we have been given with a simply supported truss which has been subjected with 4 different forces act at different points. The question is, you need to find the forces in each member of the truss, and we are going to use the method of joints. Since it is a simply supported truss, first step is we need to find the support reactions. So here this is a roller support which will have only vertical reaction, whereas this end is a pinned or hinged end which will have both the horizontal reaction as well as the vertical reaction. Before which we need to check whether the given truss is a perfect one or not. So here we have 1, 2, 3, 4, 5, 6, 7, 8 and 9 members are there. And regarding the joints, we have 1, 2, 3, 4, 5, 6 joints are there. And since we have one roller support and one pinned support, we have 3 reaction components will be there. Therefore, R is equal to 3. So now substituting this one, it satisfies the condition M plus R is equal to 2J. Hence, the given truss is a perfect truss. Now, since it is a simply supported truss, as I told, we need to find the support reactions first. So roller support will have only the vertical reaction, let it be VD, and pinned support will have both vertical reaction as well as horizontal reaction. Let me assume in this direction. Now applying the equilibrium conditions, that is forces in the trusses, both in the x direction and y direction will be equal to 0. Let me start with the horizontal force equilibrium, Fx equal to 0, in which we can see only one force is acting in the horizontal direction. There is no other forces acting in the horizontal direction for the entire truss. Therefore, Hf is equal to 0. Now, going on with the vertical force equilibrium, Fi equal to 0, we have 2 upward reactions are there and 4 downward forces are there. Let upward things be considered as positive and downward are negative. We can write Vd plus Vf minus 10, minus 40, minus 10, minus 24, which will be equal to 0. So simplifying, we'll be getting Vd plus Vf is equal to 84. So now we have a relationship only, but we don't have the values for these two. Let me go with the third equilibrium condition, that is the moment is equal to 0. So in trusses, as all the joints are considered to be pin joints, you can assume the moment is equal to 0 at any joints. For simplicity, let me assume moment about the point D is equal to 0. Now you can see that we have Vf is there. Vf will rotate about the point in the anti-clockwise direction. That will create a positive moment. Let anti-clockwise moments be positive. So in that case, Vf into the perpendicular distance. Here the force is a vertical force. The perpendicular distance will be a horizontal distance between this point and the point D. That is 6 plus 6, 12. That's what has been given. Vf into 12. Next one, I shall move with this one. Here the 10 kilonewton force. You can see that the line of action is passing through the point D. So this one will not create any moment. As well as Vd is also acting at the point D itself. Therefore, this also will not create any moment. Next, shall I move with that 40 kilonewton force. So 40 kilonewton force is acting on the right side of the point D and it tends to rotate in this direction, that is the clockwise direction. So it will create a negative moment. The force is a vertical force, then we need to multiply with the horizontal distance, the perpendicular distance. That is nothing like 6 meter. Therefore, it will be minus 40 into 6. Next, I shall move with the 10 kilonewton force. 10 kilonewton force is also acting on the right side of the point D and it tends to rotate in the clockwise direction about the point D. Let it be again negative. Right. So the value will be 10 into the vertical force multiplied with the horizontal distance. So from the point C to point D, that is nothing like 6 plus 6, which will be equal to 12 meter. So in that case, it will be minus 10 into 12. That is what has been given here, minus 10 into 12. The only thing left out is this 24 kilonewton. Again, 24 kilonewton is also acting on the right side of the point D and it is acting in the downward direction. Therefore, this also will create a clockwise moment about the point D. The value will be 24 into the perpendicular distance, horizontal distance is 6 meters. So minus 24 into 6, which will be equal to 0. Now simplifying this equation, we'll get Vf is equal to 42 kilonewton, and substituting the value of Vf in this equation, we can get the value of Vd is also equal to 42 kilonewton. So in the analysis of trusses, mark may not be awarded for finding the support reaction, because the question is you need to find the forces in each members. So in that case, first, better to check whether the given structure is symmetric as well as the loading is also symmetric or not. For example, in this case, the structure is symmetric, and going on with the loading, we can see that 10 and 10 are acting at the extreme ends. Similarly, 40 and 24 are acting exactly at the center, which means that with respect to loading also, the structure is symmetric. So in that case, Vd and Vf will take care of half of the total load which is acting on the truss. That is nothing like 84 kilonewton. So that is why it will be 42 and 42. So directly we can make a statement, since the structure is symmetric in terms of loading as well as the profile, Vf will be equal to Vd is equal to 84 by 2, which will be equal to 42. Directly you can write that one also. Right. Next, in order to find the forces in all the members, let me go with the joint equilibrium condition. We shall start with the joint A. Why we are starting with the joint A rather than going with the joint D, in the sense, we have, if you are taking joint D, 1, 2, 3 member forces are there, which are unknown. But we have only two equilibrium equation, that is Fx equal to 0 and Fy equal to 0. That is why we can't able to start with the D. Rather, we can go with the A. If you are going with the A, we have 1, 2. Only two members are there with one known force. So we can easily solve. First step is we need to assume the member forces are in tension, that is acting away from the joint. Let it be FAB along the member AB and FAD along the member AD. Right. So let me draw this joint separately here. We'll be getting the 10 kilonewtons acting downwards along the joint A, and FAD is also assumed to be acting in the downward direction. FAB is assumed to be acting in the horizontal direction right side. Now applying the equilibrium Fx equal to 0, we'll get FAB is the only force acting in the horizontal direction. Therefore, FAB is equal to 0. Now applying the vertical force, this is a 0 force. There is no force acting in this member. So this is called the zero force member, where a member carries only 0 force. It's called the zero force members. So what is the role of this zero force member is in order to provide the stability for the entire structure. For example, if this member, even though it is not carrying any force, if I am removing this member, one member will be getting eliminated from the overall structure. Thereby, the entire structure will become deficient. So that is not an acceptable case. That is the reason these members been added. Those members are called as zero force members. Next, applying the vertical force equilibrium, we have 10 is acting downward direction. FAD is also assumed to be acting in the downward direction. So solving this one, we'll be getting minus 10 kilonewton, which means that our assumed direction of the force is wrong. So it will be acting in the upward direction. That is nothing like 10 kilonewton force is compression force. That is what the assumed direction is wrong. Therefore, the force will be acting in the upward direction. That is towards the joint. Towards the joint in the sense it is compression. Next, we shall move with the next simplified joint, that is the C joint. So taking C joint, we have two members are there, CB and CF, assuming the forces are tension acting away from the joint. Now taking the joint forces separately, minus 10, FCB and FCF. Right. Applying the equilibrium equation Fx equal to 0, we'll get FCB is equal to 0. That is, again, this member is also a zero force member. Now applying the vertical force equilibrium, we'll have minus 10 minus FCF is equal to 0, from which FCF is equal to minus 10. Again, the direction assumed is wrong. It is in compression. So it will be acting in the upward direction. So now we got 1, 2, 3, 4 members being solved for the forces. So the remaining is 1, 2, 3, 4, 5 members to be found out. Next, we shall move with the joint D. So here already this force has been calculated, which is compression. That's why along this joint, the force has been taken towards the joint. Right. So now taking the joint D, we have two members to be still found out. Right. That is DB and DE. Let me assume the forces are in tension acting away from the joint, FDB and FDE. So we have the inclination theta is there. So theta can be found out because this, if we are taking this as a triangle, this is the opposite side, which is equal to 3.2 meter and the adjacent side is 6 meter. So theta will be equal to tan inverse of 3.2 divided by 6. We can able to find out the angle theta using this relationship. So that will comes around 28.07 degree. So we can substitute this value anywhere, wherever it is required. Now, taking the joint forces separately, we'll have this theta is available. Right. So substituting the equilibrium equations, we can see Fy. I'm starting with the vertical force equilibrium. So we'll have minus 10 is there, plus 42 is there. And then we have the vertical component of this force. So vertical component will be acting in the upward direction. And that value will be nothing like angle is given with respect to x-axis. Therefore, vertical component will be sine theta. Right. So we can substitute that one. 42 is acting upward, 10 is acting downwards. So plus and minus, and this vertical component will be acting upward. That is plus FDB sine theta is equal to 0. Right. So solving this equation with the theta value of 28.07, we get the value of dB as minus 68 kilonewton, which means that the member is in compression. Right. So since the direction is reversed, don't change the direction now itself. Let us solve the horizontal force equilibrium also with respect to the same joint. Once both the equilibrium equations been done, later we can change the direction based on the nature of the force. Now Fx equal to 0 means we'll have FDE will be there, and the horizontal component will be of this force will be that. That is, it will be acting in horizontal direction in the right side direction. So this component will give cos theta. So in that case, FDE plus FDB cos theta, which will be equal to 0. Substitute the value of FDB as minus 68 and cos theta is 28.07. We can get the value of FDE is 60 kilonewton tension. Now, since this is in compression, our assumed direction is wrong. So it will be acting towards the joint. Right. Next, we shall move with the joint F. This is the joint we are considering. Again, similar to the joint D, we can assume the forces which are acting away from the joint, that is in tension. And now the force has been taken. Right. Again, angle remains same. Theta is equal to 28.07 degree. And now resolving the forces, applying the equilibrium equation Fx equal to 0. The horizontal component of this FFB will be acting in the left side direction. So that component will be cos theta. So in that case, minus FFE minus FFB cos theta, which will be equal to 0. Or otherwise, since both are negative, I just consider both are positive. Right. Regarding, since both are unknown, we can't able to solve for this unknown. Let me go with the vertical force equilibrium. So in that case, we have 42 is acting upward, 10 is acting downwards, and the vertical component of this force will be acting in the upward direction, and that component will be sine theta. So it will be plus FFB sine theta. So knowing the value of theta, we can get the value of FFB, which is minus 68 kilonewton, which means this is in compression. Now substituting value of FFB as a minus 68 in this equation, we can get the value of FFE, which is 60 kilonewton tension. Now, since the direction assumed for FFB is wrong, we can change the direction which will be acting towards the joint. Now, all the member forces been calculated except this one. So, for which you can take either joint E or joint B. Since joint E is having less number of members, let us go with the joint E itself. All other things being found out. Now, again, let me assume the force is a tension which is acting away from the joint. Taking all the forces which are acting at the joint E, we have 4 forces are there. Now we can solve for the vertical force equilibrium. We'll have FEB minus 24, which will be equal to 0. So from which FEB will be calculated, which is in tension. So the assumed direction is correct. Now representing all the forces in this figure, and you are supposed to detail the forces in a tabular format also, along with the nature of the forces. That will give the perfect solution for this problem. Next, the second numerical is also remains the same. That is, we need to find the force in each members of the truss by using the method of joints. But the difference is, previous case, we had a simply supported truss. That is, one end is hinged and the other end is roller. Right. So in that case, that is a statically determinate condition. But coming on to this case, you can see both ends are pinned end, which means that we'll have vertical reaction, horizontal reaction, vertical reaction, horizontal reaction. So totally 4 unknowns will be that, which is statically indeterminate case, which can be solved by using only these equilibrium equations. Right. So in that case, you should have to solve with a different approach. As I already told, these kind of problems, marks may not be awarded for support reactions. That is the reason. For example, this problem, since we have 4 support reactions are that, we can't able to solve for this unknown. Okay, for which you can directly solve the member forces without solving for the support reactions also. That is an example of this problem. Right. So before solving this problem, as always, we need to check whether the truss is a perfect truss or not. So here, MS, we have 1, 2, 3, 4, 5, 6 members are there, and we have 1, 2, 3, 4, 5 joints are there, and since we have 2 pinned support, 4 reaction components are available. Right. Now we'll be checking this condition. M is 6, R is 4, total is 10, and 2J is 2 into 5. So both will be getting nullified. So in that case, the given truss is a perfect truss. Now, as I told, we are going to apply the joint equilibrium condition directly rather than finding out the support reactions. Okay, let me start with the joint E. So joint E, why we are starting with the joint E in the sense, we have only 2 member forces are unknown in that case. So that is the reason we are going to start with the joint E, for which we need to know the angle theta. So again, theta will be equal to tan inverse of opposite by adjacent. Opposite is this one, that is nothing like 0.9 divided by horizontal is 1.2. So solving this one, will be getting the angle as 36.87 degree. That we are going to apply for all the solution. Right. So taking the joint E, again, two members are there. Let me assume both the members are in tension, acting away from the joint, FEB and FED. Right. So now taking the joint forces alone separately, we have 3 kilonewtons acting downward. FEB and FED both are taken as a tension assumed. Right. Now applying the equilibrium equation, let me start with the vertical force equilibrium. We'll have 3 is acting downwards, and this inclined force will have the vertical component upward. That will be sine theta. So in that case, it will be minus 3 plus FEB sine theta, which will be equal to 0. So applying the value of theta as 36.87, we'll get the FEB as 5 kilonewton tension, which means that the assumed direction is correct. Next, we shall move with the horizontal force equilibrium. We have FED, which is acting in the left side direction. This will be negative, and the horizontal component of this force also will be acting towards left side. So that also will be negative, and the component will be cos theta. So in that case, minus FEB cos theta minus FED will be equal to 0. Substitute the value of FEB is equal to 5 and theta is equal to 36.87. We can get the value of FED as minus 4 kilonewton, which means that the assumed direction is wrong. The member is in compression. So change the direction, it will be acting towards the joint rather than acting away from the joint, which has been assumed. Now 2 members been done. So we are yet to complete with the 1, 2, 3, 4 members are still yet to be found out. Next, we shall move with the second joint, that is joint B. So going with the joint B, so we have 3 members are connected to joint B, in which already one has been computed, which is in tension. Whereas the other 2 are unknown, and we have one external forces acting 6 kN in the downward direction. Now again, assuming these 2 members are in tension, acting away from the joint, FBA and FBD, taking those joint alone separately, we'll have 6 kilonewtons acting downward, FBA is acting left side, FBD is acting downwards, and phi, it is in inclined direction, which is in tension, making an angle theta. Theta is 36.87. Now applying the equilibrium equation Fx equal to 0, we'll have this one negative since it is acting left side, and this component will be, horizontal component will be acting towards the right side, and that will be cos theta. So in that case, minus FBA plus phi cos theta, which will be equal to 0, and theta is, remember, 36.87. So substituting this value, we can get the value of FBA as 4 kilonewton, which is in tension. So assumed direction is correct. Next, we shall move the vertical force equilibrium. We'll have minus 6 is that, minus FBD is that, and the vertical component of this force, which will be acting in the downward direction, and this will be sine theta. So this will be negative also, since it is acting in the downward direction. Therefore, it will be minus 6 acting downwards, minus FBD downwards, minus phi sine theta, which will be equal to 0. Theta is known, 36.87. Substituting the value, we will be getting FBD as minus 9 kilonewton, which means the assumed direction is wrong. So the member is in compression. So change the direction, which will be acting towards the joint since it is in compression. Right. So now we have 1, 2, 3, 4 members being calculated. Remaining is 1 and 2. These 2 are yet to be found out. Next, we shall move with the joint D. If you are taking joint D, we have 1, 2, 3, 4 members are connected. There is no external forces acting at the joint D. And out of which 4 members, already 2 members been calculated, that is DE and DB. So DE, DB both are in compression since the forces are acting towards the joint. And we are going to assume these 2 members, that is AD and CD, to be in tension, acting away from the joint. Let it be FDA and FDC. So taking the forces which are acting at the joint D separately, we'll have minus 9 kilonewton. FDC is left side, FDA is also left side inclined, and we have minus 4. Left side, it is 4. Right. So now applying the equilibrium equations Fx equal to 0, we have minus 4 is that, minus FDC is that, and DA will have the horizontal component which will be acting towards left side. That will have the cos theta component. Okay. So in that case, it will be minus FDA cos theta minus FDC minus 4 is equal to 0. And since both are unknown, we can't able to solve for this one. DC is it DC? DA. I'm sorry, this has not been calculated as of now. We need to go with the vertical force equilibrium first. So minus 9 and then we have the vertical component of this FDA, which will be acting in the upward direction. That will give the sine component. So it will be minus 9 plus FDA sine theta, which will be equal to 0. So theta is known. Substituting this one, we can get the value of FDA, which is 15 kilonewton tension. The assumed direction is correct. Now this DA value of 15 to be substituted here, and then only we can able to find out the FDC, which is in compression. Since it is negative value, you will be getting. Okay. So our assumed direction is wrong. It will be acting towards the joint. Now all the members, the force has been computed. Okay. So this is what is the final diagram representing the forces in each members, as well as the table detailing the forces in the members and their nature also. So to summarize today's lecture, a truss is a pin-jointed framework carrying axial forces only. Truss analysis require idealizing assumptions. Static determinacy must be checked before any analysis. And the method of joints applies equilibrium at each joint, which is suitable for finding forces in all members. And members forces can be either tension or in compression. In the next lecture, we'll continue truss analysis using the method of sections, which is faster when only a few member forces are required. Thank you.